Hello and welcome everyone. My name is Samuel Chen. I'm from Wells Fargo. Today, I'm thrilled to present to you my latest research on the quantum deep recurrent reinforcement learning. In this presentation, we will cover the following topics. We will first provide a brief overview of quantum computing and its application in machine learning and the motivation for quantum deep recurrent reinforcement learning. Then I will provide some basic concept of what is a reinforcement learning, and then our building blocks for today's recurrent reinforcement learning, namely the quantum version of the long short-term memory. I will introduce the architecture of the QLSTM and how the QLSTM can be used for quantum machine learning tasks. Then we will combine the QLSTM with the reinforcement algorithm to develop the quantum deep recurrent reinforcement learning algorithms. I will show numerical simulations to verify the proposed ideas. Finally, I will provide some conclusion of today's talk. The achievements of AlphaGo in the 2016 drew a significant attention to the development of artificial intelligence and the machine learning techniques. One of the critical parts in the success of AlphaGo is the deep reinforcement learning. Meanwhile, the development in quantum computing hardware is also very significant. Since 2016, IBM provides cloud-based access to real quantum computers. And today, many big companies and startups are working on delivering larger and larger scale quantum computers. For example, IBM announced 433 qubit machine last November. With the great achievements in both reinforcement and the quantum computing hardware, we may ask, can we merge these two fascinating technologies? For example, an reinforcement algorithm running on a quantum computer? Among various proposals, variational quantum circuit is the leading method to build quantum machine learning, including quantum reinforcement learning. There are three categories of reinforcement learning. Supervised learning is a type of machine learning where the algorithm is trained on labeled dataset. The goal of the algorithm is to learn a mapping between inputs and outputs that can be used to predict the output for new unseen inputs. For example, the image classification. A supervised learning algorithm is trained on the labeled dataset of images and their corresponding labels. Just imagine the cat virtual stocks classifiers. Unsupervised learning, on the other hand, is a type of machine learning where the algorithm is not given labeled data. The goal of the algorithm is to find patterns or structure in the data. For example, in clustering, an unsupervised learning algorithm groups similar data points together. In the reinforcement learning, the algorithm learns by interacting with the environment and receiving feedback in the form of rewards or penalties. RL is a type of machine learning that is based on learning from experience, where supervised and unsupervised learning are based on learning from labeled and unlabeled data, respectively. RL is the type of machine learning that enables an agent to learn by interacting with the environment. The environment consists of a set of states, actions, and transition probabilities. At each time step, the agent observes the current state of the environment and selects an action to perform based on its policy. The environment then transitions to a new state and provides the agent with a reward signal that reflects the quality of the action taken. The agent's goal is to learn the policy that maximizes the cumulative reward over time. The RL agent itself can be a deep neural network or a variational quantum circuit. In the machine learning, recurrent neural networks, RNN, are designed to process sequential data. The general idea is that given the input X at the time step T, the output at time T is fed back into the neural network to predict the next time step T plus 1. It means that the model can keep some form of the earlier information, that is, retaining certain memory. However, the RNN suffers from several problems, such as vanishing gradient. The long short-term memory, LSTM, is a modifier of RNN to fix these issues. It processes the cell states to keep track of the long-term dependencies and reduce the vanishing gradient problems. The quantum LSTM, which the classical neural networks W replaced by variational quantum circuit, has been shown to be very successful in several time series modeling tasks. The building blocks of the QLSTM is the variational quantum circuit. The variational quantum circuits include three components, namely the encoding circuit, the variational circuit, which is the actual learning part, and the final quantum measurement. We employ the hybrid quantum classical paradigm. Basically, the computational tasks are divided into two parts. The easiest part can be done on the classical computer, while certain hard computational tasks are carried out on a quantum computer. With this framework, we can easily apply the optimization method developed in classical machine learning community. The quantum LSTM model can be optimized through this hybrid model. Let's put all the components together. To build a quantum reinforced learning capable of memorizing previous steps, we combine the quantum LSTM and the deep Q learning algorithms. The goal is to leverage the potential quantum advantage provided by the QLSTM to learn how to solve a particular task, which may be only partially observable. For the testing cases considered in this work, we choose the standard CarPro environment. The observation is a four-dimensional vector comprising values of the car position, velocity, pole angle, and the pole velocity at the top. For partially observable cases, we consider the first three dimensions only. Through numerical simulations, we show that in both the fully observable and partially observable cases, the QLSTM-based deep RL outperform the classical counterparts. Here, we consider the classical counterparts to be RL models equipped with classical LSTM models with similar model architecture and model size. The model size here means the number of parameters. We can see that the quantum version of RL can reach higher and more stable scores. The quantum recurrent neural networks can be used to further enhance the quantum reinforcement learning. QRNN models such as QLSTM can be used to improve the QRL in partially observable environments. QLSTM-based QRL can outperform classical LSTM RL agent with similar number of model parameters. Thank you. Thank you for listening to my talk.